Okay, I see David. I still don't see Bob.
This is David.
Hi, David. While we're waiting for Bob, I don't think he's joined yet. I think we can complete the agenda bashing. So this is the agenda that I'm sharing now that we plan to use today. And does anyone want to make changes to it? Speak now or we'll proceed.
The only comment I think I'd make on the agenda is that we want to be generous to some congestion experienced folks, because we've cut them short a number of times in the past, and it'd be nice to balance things slightly here. So about 30 minutes. It runs long. It runs a bit long. Make sense?
Yeah. So that said, do you want to proceed to talk about the plan for Vancouver?
Right.
I have your charts. I can share them.
I believe I can get my charts up and share them. Give me a minute here.
Okay.
Find out when this works or not.
So sorry, I'm late. One more comment on the agenda. Just want to mention that at least I don't see if Magnus is in the meeting, but like we have to disappear in our. So if there's anything that needs like AD attention, it would make sense to have it earlier than later.
It's one of the reasons for starting with these slides.
That makes sense.
All right. I think we've given people the customary 3 minutes. Should we go ahead and get started?
I think so. Yes.
All right. So title is ECT1 and the internet. I'm speaking on behalf of all the TSVWG chairs. However, the usual disclaimer responsibility applies. All the good stuff in here is shared responsibility. The disastrous, obvious mistakes are solely my doing. Okay, this is the usual note well slide. This is an IETF meeting. The note well procedures apply. So the chairs have been trying to figure out what our path forward looks like. And this Winston Churchill quote seemed to be a pretty good description of where we find ourselves. This is not the end. It's not even the beginning of the end. It is perhaps the end of the beginning. So what do we think the end of the beginning might look like? Backing off from the technical details of both proposals, SCE and L4S, which are important, there's a core decision that needs to be made about ECT, how ECT1 is going to be used in the internet. In the issue tracker, this is issue number 20, although you'll see in a minute that we plan to frame it a bit differently. We propose to make that decision in Vancouver, which raises the question of what exactly is to be decided. So would like to suggest to the working group that the end of the beginning consists of agreeing on the decision to be made. And with that suggestion, let me see if I can get this thing out of the way there. The next two slides are the initial attempt by your hardworking working group chairs to state the decision. The goal of our meeting is to get to some rough consensus on the decision to be made. It is not a goal of this meeting to actually make the decision, and would very much ask that people keep that in mind in looking at the slides, because what we are currently planning or hoping to do in Vancouver is to start with revised versions of the next two slides, allow both of the proposed experiments, LFRS and SCE, each present a few slides on what they think is the best use of ECT1 for the internet as a whole. The chairs plan to set time and content guidelines for those few slides, review and post at least a week in advance, after which we get to frame and moderate the Vancouver meeting discussion, beyond which we hope a small miracle happens and we actually make a decision. This is wishful thinking, but we need to be optimistic. For now, we're going to review the next two slides for content and not attempt to make the decision now. Let me pause here and take questions on what happens next before I put up the slides that are going to be the real piece of fun. Any questions, comments? Okay, for the North Americans, we can say the coffee's not working, but I'm impressed that I don't hear anything yet. All right, continuing. This is, hang on. This is the proposed first slide for Vancouver, which is our attempt to frame the decision, and we're framing the decision around the ECT1 code point. Let me walk through this slide and describe a few subtleties. So the background here is RFC 4774, which is a document on specifying alternative semantics for the condition notification field. At the time 4774 was published, it assumed that DSCP would be used as a signal for alternate ECN semantics. We now have two proposals that are planning to use the ECT1 code point as that signal. And the decision that we think the working group should be making is, how does ECT1 signal alternate ECN semantics to the network? Is it an input, for example, as used by L4S as a classifier for queue selection, or is it an output, for example, an indication of lesser degree of queue congestion as SCE does? And internet scope, we believe that choosing both is not viable. Not on the slide, but an unfortunately very possible outcome of trying to have it both ways is we lose the code point in that it remains experimental forever. Any comments or questions on the content of this slide? I would point out that the EGs here in A and B are very important, because decisions being made is, how is it being used? This doesn't automatically approve the corresponding proposal going forward, but it gives you some indication which way the wind is blowing.
Looks fine from our perspective as a statement of the problem.
Is Bob on yet? All right, not hearing any objection.
Bob shows up as muted, David. But he does show up as connected with audio. One thing I would also note is maybe for sort of things that need area director attention is, the assumption here is that we can only do one or the other of L4S, and that the working group can't do both because it's not viable for the internet. So I think that's maybe, while we have some AD presence here, it's useful to make sure that's understood, that that's the assumption going in.
Maybe a remark from me, Koen de Schepper. Do I understand the decision between A and B, if you say it's purely input or output? Of course, both have consequences, and do we take into account the consequences as well? Or is it, I mean, it needs to be founded on some mechanism behind it that is provable to work, no?
Let me choose my words carefully in answering the question. What I would say is that this decision cannot be made in isolation. It needs to be made with an understanding of the likely consequences, which are given in the EGs that follow that follow each choice. I'm trying to split a hair here in that if one chooses, say, input, that means that the L4S proposal is favored going forward, but it doesn't automatically approve L4S. I hope that distinction's clear.
Okay, but it's in the scope of the proposals which are behind that mechanism,
Yes.
right?
Yes, in particular, it is fine to discuss the consequences and the merits of the consequences in Vancouver, not here.
Okay.
So just for clarification, I understand that the decision is between input and output, and it makes sense. We want to make any decision about what is really the semantic of the input.
That decision gets made in the context of discussing the specific proposal to use it, which is what the working group proceeds to next after making that decision. The decision is broader scope. I mean, particularly see the comment I sent to the mailing list about how whatever we do here and move forward, even if it doesn't pan out, it's going to leave behind running code that knows how that knows what decision was made here, and that's going to be with us for a while.
One other comment is that both alternatives could be L4S could be made compatible with both alternatives.
Who is speaking there?
Steve Blake.
All right. I would be interested to hear what the L4S folks think. I see a question from Sebastian. Could we require to couple any ECT1 overloading with a DSCP? That's an interesting question. My personal opinion, and this is now not speaking as working group chair, is I don't believe either L4S or SCE wants to do that.
Maybe Gori adding in here, if they do want to do it, then there is a process for doing this. So this is totally okay if the proponents of one of the schemes decide that that's the way they wish to go.
Agreed. However, I know at least in the context of L4S, there was an individual draft that was digging in this area, and it's basically been abandoned. And I hope I'm not putting words into Bob Briscoe's mouth by saying that. Bob, can you speak to us, or do I need to try to relay stuff off a chat?
Well, I can't hear Bob. Can you hear me?
I can definitely hear you, and I cannot hear Bob. I can't hear Bob either.
David, this is Jake Holland. Can I ask, is the intent here for the decision not to apply to a DSCP scoped deployment going forward?
If someone wants to do a DSCP scoped deployment, I think we're in a different place with that, as Gori sort of as Gori summarized, which is that if you go forward with a DSCP based deployment, then RFC 4774 is your friend, and it's relatively straightforward to figure out what we're trying to do. You will, however, have interesting running code issues with the common practice of bleaching DSCPs to 0 at network or autonomous system boundaries.
Yep. Noted. Thank you.
This is Steve Blake again. Can I make another comment?
Sure.
Deploying any of these schemes requires changing the data path and configuration of network nodes. So any current practice around what happens with DSCPs I question the relevance, considering anybody deploying either one of these experiments is going to have to be tinkering with these boxes.
That's actually a good segue to the next slide. Can you hold that thought, and let's bring it back up on the next slide. Bob, have you got an ability to say anything yet, or at least type something in the chat? All right. All right, let me go. Since Steve has sort of invited us to go to the next slide, let me bring up the next slide, which I think speaks to his point. The chairs thought it was important enough to go ahead and include this as part of the decision. So the title of the slide is Friendly Coexistence with Competing Traffic. And we observe that both proposals have chosen option 3 from RFC 4774 about how traffic using the new ECN semantics interacts with traffic that doesn't. Now, the full name of RFC 4774 option 3, which is section 4.3 of RFC 4774, is Incremental Deployment Option 3, Friendly Coexistence with Competing Traffic. And for the purpose of clarity, or at least motivating what's going on here, the competing traffic that's interesting is that which uses existing TCP congestion control, such as Reno or Cubic, and the coexistence focus is at unmodified nodes, since this is going to be let loose on the entire internet, and in particular shared bottleneck queues with the ECN AQM. The reason this focus is that fair queuing network nodes don't have coexistence problems. They very cleanly separate the traffic, the competing traffic out into separate queue instances and deal with it quite nicely. The scenario that is important for this slide is traffic competition at a shared bottleneck queue with the ECN AQM. Starvation of one class of traffic is not an acceptable outcome. And in this scenario, if you don't have starvation, the competing traffic, which is using TCP congestion control such as Reno or Cubic, drives the bottleneck queue occupancy level. And both proposals need to explain how to deal with this scenario in order to move forward. Steve, I hope this provides some perspective on your comment. On your comment. Okay, this is the second slide we propose to use in Vancouver. Anybody see some edits that ought to be made?
It looks good from our end.
Is that cough a cough, or is that an editorial comment?
It's a compliment.
This is Jake Holland again. I'm not sure. Is this saying that FQ network that FairQ is out of scope here? I'm not quite sure it's accurate to say there's no coexistence problems. I think that building a standing queue, even in an FQ, for example, could be considered sort of a problem. There can be hash bucket collisions and such, but I think you're saying that these should be de-emphasized in terms of the decision focus?
I think so. Would it be better if it said not a significant cause of coexistence problems?
Slightly.
Or am I trying to split things too finely there?
I'm actually not sure I understand this point at all, because I mean, it's only not a problem if you know that the bottleneck uses FQ, right? But how do you know that?
You don't. And the point
So,
is
yeah.
that and the point, Miriam, is exactly that the
Okay.
the discussion needs to whoops, what did I do there? Sorry. The discussion needs to focus on the shared bottleneck queue, because that's where
Okay.
the big problems are. The FQ network nodes are not a cause of big problems.
Okay, then I just completely misunderstood this sub-bullet point, and you might need to rephrase.
In which case, I definitely need to edit it. Let me go do that right now.
While David's editing, so he can think, it's Gary here. I'm not convinced that this is a showstopper. I'm convinced it's something we need to think carefully about and write some text about. If we really are deploying a new technology in an experimental case, then we might want to make some decisions here, but we can't just do that without considering it.
And that was my intent in writing the slide. It was not that this is a showstopper or something that causes one of the proposals to be completely untenable. It is rather asserting that this topic has to be dealt with and that the proposals are expected to deal with it.
David, this is Steve. My only comment was that the statement that routers currently bleach DSCP bits is true, but routers currently don't implement either one of these schemes. So routers will have to change, and configuration of routers will have to change.
Okay, Gary here. Well, good thinking again, because what you say is true. However, we will have routers that haven't changed on the path, and we should expect them.
What Gory said.
That's correct.
Rod asked, can I get clarification on what is starvation? Holy smokes, my immediate reaction is we know it when we see it.
David, I would recommend we take that offline, and these are out now. People can look at them. We can talk about them between now and Vancouver on the mailing list if we're mostly agreed that this is a fine path to take for the working group. And I would suggest that we move on and start talking about SCE.
I think that's a fine path forward. I will post the slides with the edit I just made after this meeting.
Very good.
Let me write a note to myself to make sure I remember to do this.
And while we transition, would someone else like to show the SCE slides, or should I try to share them from here?
We might try doing it from this end. It's not something we've tried doing before.
That lets you control which chart we're on rather than having to prompt me. So if you want to, go for it. Otherwise, I can show them from here.
Let me see if I can find the right option in a minute or so.
Wes, while you're doing it, can I just check that people can hear me now? This is Bob, even though I can present later.
Yes, you sounded good from here.
There's an echo on the line somewhere, but we can't hear you.
Yeah, that's probably because I'm on my phone. I'll go and get a headset.
Right, I think I can share this screen and make it full screen. And right, can you see that?
Yeah, looks good.
Okay, excellent. Let's get started. Right, so as David Black's framing of the question notes, it is up to each proposal to show the utility and safety of their particular use of the ECT1 code point. Obviously, we're not expecting a decision to be made today, but we prepared this, this slide set before those slides were put up. So I believe SCE is in a good position to do so after about a year of actively working on this particular problem. We didn't get much time to show that in Singapore, so we're grateful to have this opportunity instead. So we'll start with outlining the problem as we see it, the proposed signaling mechanism and its operating principles, then briefly present some new work as part of showing how SCE traffic and infrastructure coexists with existing internet traffic and infrastructure. Then we have some material which may highlight some surprising results as we test SCE implementations against the Prague requirements and some of the difficult environments that congestion control algorithms and new protocols are supposed to be able to accommodate. So you'll be seeing a lot of this type of graph in this slide deck. This one shows the current RFC compliant state of the art. It's a cubic flow encountering a caudal equipped bottleneck. The baseline latency is 80 milliseconds round trip, which is typical for internet class. And you can see that there are small excursions above that by just a few milliseconds as cubic probes for capacity, which in this case is 50 megabits a second. And cubic receives CE marks to tell it to back off at the peaks of the latency. Overall, cubic is using maybe 90% of available capacity on average, much more than Reno would, and of course, a drop-tail FIFO would look far worse in terms of latency. And we know this works well in practice on the public internet. In fact, we're using something very like this to talk to you right now. But can we improve the link utilization and remove those latencies? That's the question. And here is our approach to solving it. We start from a foundation of safe compatibility with existing transports and networks. This gives us a robust platform on which to innovate, with no ambiguity of what's expected at any point in the system. A bit of history. In the late 1980s, VJ established that packet loss was a congestion signal. It's still often the only available signal that can reliably be detected and interpreted. On this, the familiar AIMD sawtooth pattern emerged. At the time, packet queues were typically only 8 packets long, but hardware vendors soon learned that deeper buffers increased throughput at the expense of latency. So ECN was introduced so that signaling congestion no longer required dropping packets. Dropping packets wastes capacity and incurs application latency through retransmission. AQL algorithms then appeared which could reduce latency without destroying the ability of the queue to absorb bursts. Deployment has been slow, but is now significant. ECN's congestion experience marks are a reliable mechanism in TCP due to the sticky ECE CWR flags feedback. This also makes it imprecise and heavy-handed. ECE, by contrast, is fed back precisely but unreliably through an additional flag. ECE itself is the hitherto spare ECT1 code. It's an unambiguous output signal from the network. And by keeping the definition of ECT0 and CE this way, we not only ensure backwards compatibility with existing receivers, who will treat ECT1 as synonymous with ECT0, but we can also respond compatibly to congestion experience signals can be produced by existing AQMs. This is absolutely fundamental to SCE's design and has not changed since a year ago when we first presented it. Some of the details have changed. Now, comparing this with the way L4S works, we can see some clear parallels. Each SCE mark is semantically similar to each L4S CE mark. The same end result is achievable with either signaling system, assuming they operate in isolation and on a steady path. But you can see that L4S would have more difficulty fitting into the same network as RFC 3168 ECN traffic, corresponding to a sharp decrease in capacity. Perhaps we will hear how they tackle those problems later in this meeting. To reiterate, SCE retains the normal ECN signaling in its entirety. The sender marks outgoing traffic with ECT0, informing the network that it will correctly process a CE mark. The middle box may then signal CE, the receiver will inform the sender with ECE, and the sender acts with congestion window reduced. And there are even specifications on how much it should be reduced. So SCE is transparently compatible with existing middle boxes and receivers, and has an easy way to be informed of large capacity reduction. Also, if something were to disrupt the SCE signaling, the CE mark remains as a failsafe. And SCE can also be signaled by a middle box. This would be ignored by existing receivers, but SCE receivers echo it in the ESCE flag in TCP hacks. ESCE is not a sticky flag, so it is not reliably delivered like ECE, but it is more precise since it can reflect many SCE marks per RTT. Incidentally, existing senders would ignore ESCE flags. We consider that disruption to the ESCE signal, for example by ACK filtering, that introduces as much as 100% relative error, is tolerable by SCE's control loop. So here we have some basic test scenarios demonstrating SCE signaling in action. Network conditions are the same as in the first slide, except that we now have SCE-aware endpoints and a middle box on which we can turn SCE signaling on and off at will. The test starts with it on, but we turned it off for the middle part of this test to show the difference. And you can see that SCE achieves 100% link utilization with no sawtooth, no jitter, and about half the peak latency, even during flow startup where you would usually see a large latency spike induced by slow start. More importantly, the shift between signaling mechanisms is completely seamless, stabilizing reliably within one sawtooth period. And the following chart illustrates the actual signaling.
Hi, this is Pete Heist. So what we're looking at here is the bottleneck shift in signaling that's going on. So the yellow traces show the proportion of SCE marks. And you can see the SCE marks in the beginning as the control loop stabilizes. And then you switch to the RFC 3168 bottleneck, and you've got, they're a little small, but they're red CE marks at the bottom that show where the latency peaks occur. And then we transition back to the SCE bottleneck, and we have a little spike in SCE marking in the beginning, and then the control loop stabilizes and the flow continues.
The next test has to do with capacity reduction. Steady state conditions are all very well, but the internet is not so forgiving. At minimum, we should expect a competing flow, or 10, to start up and share our bottleneck. We simulated this with a 10% and a 90% reduction in path capacity, followed sometime later with restoration. And here we see the 10% reduction, which SCE flows achieve entirely through SCE signaling in this particular case, and without a noticeable change in latency. For these tests, we used Reno SCE instead of cubic SCE, but you should expect similar performance from the latter. And looking at the signaling, you can see that there are no CE marks except right at the beginning for exiting slow start. There's just a slight peak in the SCE signaling at the beginning of the capacity reduction. And when we do a 90% reduction in capacity, there are some latency effects, and this does actually require some CE marks in order to do the reduction. But since we have CE marks, the SCE flow, the SCE sender knows to do a big reduction, and this is done entirely transparently. And there are some latency effects, but honestly, this is a pretty clean response to a severe event. And it also recovers cleanly when the capacity returns. We look at the signaling, and we can see that there is a large peak in the SCE marking, and we can also see a significant amount of CE marking accompanying that, along with some CWR responses around here. Yeah. Little green ticks. But then it stabilizes, and we have steady SCE marking, which then goes away to signify that the capacity has been restored. We did also put L4S through this test. The results were not so good. And there is, of course, a possibility that there's some code we haven't yet seen yet that might improve this case. And we're happy to discuss this offline. So for coexistence with non-SCE traffic, so first let me emphasize that when SCE traffic meets existing infrastructure, such as a drop-tail FIFO, a dropping AQM, or an RS3168 AQM, it behaves just like any other conventional TCP deployed today. So this means SCE endpoints can safely be deployed on existing networks. Obviously, we'll go into more detail on that in Vancouver. Now, when an SCE middle box is deployed, that is where coexistence with conventional traffic has to be addressed somehow. Now, obviously, fair queuing works. But single queues with single AQMs are problematic, as they tend to squeeze out the SCE flows. As you may know, I developed the Cape Q disk with some other people, basically FQ Cordel on some serious steroids. As a simpler and perhaps easier option for hardware people, I've also come up with lightweight fair queuing, and which we see in action here.
Okay, so what we're looking at here is when you see the throughputs here, I should point out that you're looking at the kernel's delivery rate. So that's a bit more accurate with these tight control loops than what you could see from NetPerf's throughput results. So this is a cubic flow starting up, and then after 10 seconds or so, a cubic SCE flow starting up. And that traces in orange. So you can see that as the cubic flow in green has its drops in link utilization, the cubic SCE flow fills in those gaps. And you can also see in the TCP RTT that the cubic SCE flow maintains a little bit lower latency and is somewhat isolated from the cubic flow.
So the basic logic is that FIFOs are expensive in hardware, but by recirculating packets, we can get away with just a few of them, thereby making it easier to implement. And we still have almost identical behavior to the well-known DRR++. Now, for those cases where even LFQ is too much, we stumbled across a technique called approximate fairness, which is implemented in certain high-end Cisco hardware. And so this is a technique that's known to work up to 100 gigabits a second. So this biases the congestion signals of different flows based on their relative occupancy of a single queue. Most of the required information was already present in our earlier CNQ, that is cheap nasty queuing implementation. So we extended it to produce what might be the most awesome concatenation of abbreviations of this call. Cheap and nasty queuing with controlled delay, approximate fairness. And incidentally, it is a working solution to the single or dual queue coexistence problem, of which much has been made in the past, and which will be important in Vancouver. So like CNQ, there is still a sparse flow optimization for stuff like NTP, DNS, three-way handshakes, and so on. But the clever stuff is in the bulk queue, which both flows seen here occupy. Green is again plain cubic, and orange is again cubic SCE. The fairness isn't perfect, but it's a long way from starvation, and the SCE flow is actually filling in gaps left by the sawtooth, as with LFQ, as we saw earlier. In fact, the ratio of throughput is equal to the ratio of target queue depth. Now, we've published a draft describing CODL AF yesterday, so I would encourage you to read that when you have time. Moving on to the Prague Requirements. As it happens, Pete and I are calling in from the Czech Republic, having convened at his place to prepare for this meeting. In general, most of the requirements are met by design, or by inheritance from the Linux and FreeBSD network stacks. We think we're doing pretty reasonably well on scalability and RTT independence, in that we're at least equal to the best conventional TCPs, particularly cubic. Fundamentally, a window-based algorithm will always have an inverse dependence on RTT. So to move beyond that, we have to look into rate-based algorithms. BBR offers an example here, but really that field is ICCRG material rather than TSV.
Jonathan, can I ask you a question on that previous chart? So I'm trying to understand the SCE fulfillment sort of column here. How much of it is SCE, the end host behavior that you've defined, versus dependency on the several different queue management schemes you've analyzed in combination with SCE? I'm trying to understand whether the signaling that happens in the network is decoupled from the host behavior, or if there's some assumptions about what's happening that these yeses require to be in place.
Okay, so let me see. I mean, a good deal of this comes from the signaling mechanism itself. The robustness of it allows us to fall back to multiplicative decrease reliably when we encounter legacy bottlenecks or existing bottlenecks in existing infrastructure.
So for instance, like the RTT dependence, how much of that is your end host behavior versus something that's happening in the network?
Right. Well, the RTT dependence is one of these mathematically fundamental things. So when you have a window-based congestion control, you're obviously sending a certain amount of data, the size of the congestion window per RTT. And obviously, if the RTT is longer, then your throughput will be lower by the same amount.
Oh, so you're saying here that you don't do anything about that?
Not yet, not specifically, but we do implement cubic. We have adapted cubic, and so we're at least as good as that, which is an improvement over Reno, for example.
Okay, I think I understand you better now.
But again, as I said, in order to move beyond RTT dependence, we would have to look at things like a rate-based control rather than a window-based control.
Which is going to happen in the end host, not anything in the queuing behavior.
Correct.
Yeah.
And that's something we're still looking into rather than presenting now. So our approach to scalable throughput is simply to implement cubic and to adapt cubic to understand SCE signals. Now, cubic was, of course, designed to deal with long, fat networks, as they used to be called. And what we do on an SCE mark is simply reset the polynomial growth curve to its inflection point, putting it at the current congestion window and the current time. And then we apply the usual SCE response to both the current congestion window and the inflection point level. And this, we find, works pretty well. So some test results in about the long fat networks. First, we see what DC-TCP makes of it. And that's a congestion control using linear growth. And we can see that it is getting nowhere near the 250 megabit per second capacity when we give it a satellite grade 500 millisecond RTT to contend with. This is a fairly unusual and extreme network condition, but it can exist. If we move on to a cubic congestion control, this is with conventional CE signaling, we can see improved throughput. It still takes a little while to get there, and the sawtooth has a pretty long period of about 50 seconds. And then we add the SCE support. And I don't think there's any argument that this is an improvement. Another difficult environment we would like to emphasize is bursty networks. And these happen particularly when you have a wireless link on the path. This could be Wi-Fi, 3G, LTE, probably even 5G. There will be some burstiness, and high fidelity congestion control tends to overreact to this. Now, queues are meant to absorb bursts and to meter them out more smoothly. But the high fidelity congestion control wants to signal even short-term differences in queue depth. So we showed at the Singapore hackathon that using COD-L4 as an SCE marking schedule could improve matters, and research is ongoing into the specifics of this. And of course, our next steps are continuing towards working group adoption. This meeting is a very important step, and so will the discussion at Vancouver. And we will continue testing and research into the areas previously mentioned. So, thank you for listening. And need to. Does anyone have any questions?
Jonathan, there were a couple of questions on the chat. You were speaking.
Okay, I haven't seen those just yet. I'm still trying to figure out how to turn the screen sharing back on.
Well, I can ask one of them. I guess it wasn't written as a question, it's more as a statement, but the LFQ mechanism, to me, doesn't seem to be possible in hardware queues. You describe it as requiring FIFOs, which hardware queues generally are FIFOs. But my understanding of LFQ is does not use FIFOs. It uses queues that where the hardware presumably would be able to reach into the queue to some arbitrary place, pull packets out from mid-queue to transmit.
Right, I see that objection, and you'll notice that we mentioned having 3 FIFOs, and the idea is that we recirculate the packets rather than pulling stuff out of the middle. And having 3 FIFOs makes that relatively efficient, as opposed to having only 2, one being for the sparse queue and one for the bulk queue. By having a 3rd queue, we have an efficient way of recirculating the bulk queue. And then we're only pulling from the head of any particular FIFO, and only inserting at the tail.
So at DQ time, the hardware has to potentially queue a whole series of packets out of the bulk queue and re-enqueue them into another hardware queue until it gets to the packet it's looking for. Is that correct?
Right. The recirculation does still have some overhead, and it's not ideal, but we think it's easier to implement than DR++. And again, if people still think that's too much difficulty, then we now have Coddle AF as an alternative.
Yeah, so going on to Coddle AF, the results to me look like it eliminated the latency benefit for SCE. Right, both traditional congestion flow and the SE flow had the exact same latency performance, and on top of that, it provided unfair bandwidth to the.
Right. With the in terms of the latency benefit, the thing here is that we have a single queue, so we do have fate sharing in terms of latency. And I think that was alluded to in David Black's slide 2. So
yeah, it was. I mean, there's a no free lunch principle here, which is that if you put Reno and better traffic in the same queue and you don't starve out the Reno and get it to go away, Reno is going to set the queue the queue operating depth.
Correct.
Right. So what's the advantage of the CNQ Coddle AF rather than just doing a single queue and have traditional fairness between flows and the same fate sharing?
Again, SCE is making use of capacity that was left over by the conventional flow. That's not quite so obvious as in the LFQ flow, where where they're sharing equally at some point. But believe the total capacity utilization is higher than it would be with two conventional flows. Now, we do also see that the SCE flow is running at a lower throughput than the conventional flow. And that's because it is being controlled to a lower latency level, but then Coddle AF is having to compensate by biasing the congestion signals of both flows. And that's the result. The throughput is in the same ratio as the latency targets. And the result then is that if you have all SCE flows, then the overall latency is still reduced.
I see.
Silence. We're about to lose the ADs. Any last words of wisdom from the ADs?
I didn't think I have anything to add here. Thank you for asking.
Thank you for taking the time to attend this meeting.
I think I got some of the presentation, but I'm interested really on how it compares in terms of latency rather than efficiency. Was that something that you could point to a particular graph to explain, or just recap so I kind of got how this is comparing with the latency when you're using SCE, really, I guess?
I'm sorry, I couldn't make that out.
Okay, so I was looking for a little bit more detail about how latency was impacted. I'm not particularly interested in whether you get throughput, but I am very interested in whether you get latency reduction from the other methods. And you seem to be saying some of this, but I didn't quite get it. Could you say more about that?
Okay, I think you're asking about how we achieve the lower latency.
Yeah.
So basically, because we have a finer grained control loop, we're able to select a lower latency target without losing throughput. And again, it's because we eliminate the sawtooth, so we don't have to compromise the peak latency in order to achieve good link utilization.
If it helps, Ori may be asking about what do you need to do in the network to achieve lower latency for the SCE flows under what assumptions about competing traffic?
Well, the best option is to implement some version of fair queuing. But, you know, that's usually the best option. But we can see some benefits even with Coddle AF, for example.
Okay.
I'm sure.
Can you go down the approach without queuing?
I think this is something we can profitably discuss offline.
Sure, that's fine. I'm looking for data.
Okay.
I think one more comment maybe that I would make is just that with Coddle AF or any single queue, which obviously in a single queue there is no such thing as flow isolation. We view that as also a way to transition where you have SCE flows, and as you increase the number of SCE flows, you can should be able to utilize more of the link, and then eventually when there are all SCE flows, they should have lower latency overall. So it's more of a gradual transition in the case of a single queue.
Yes, it's an approach to incremental deployment.
Can I come in on that point, that no one's going to incrementally deploy something if it doesn't work until everyone's deployed it. It's got to work when you start deploying it. Otherwise, no one's going to invest in it, and so on.
Well, naturally, that's something we are paying attention to.
No, I'm pointing out you're not. That's the point. You're not paying attention to that because you're saying that incremental deployment is good when you get nothing at the start, and that's not the point.
Well, that's false that you get nothing at the start, because we've shown that you get increased link utilization, and when there are FQ bottlenecks, there is a benefit. And so it's false to say that there's no benefit from the start.
I didn't say no benefit. I said if you don't get enough benefit. There's been years of experience of how you get things deployed. Yeah, but let's move on, maybe.
Yeah, let's.
Okay, well,
I'm getting a lot of noise from somewhere.
We view it as, compared to the FIFOs that exist today, when we at least get CODL deployed and we get latency down to, let's say, 4 or 5 milliseconds, getting an extra 2 or 3, that's going to be great too. But the important part is that we have a safe foundation to build on. And yes, we're not saying that this is the end-all answer to getting absolute low latency in 1 or 2 queues, but we're saying this is a start, this is a transition, and we can go from there. But it's a non-starter if it's not safe.
Reiterate some comments that were made on the chat, and I think also maybe helps address Gory's comment. It strikes me that the data that you're presenting is somewhat anecdotal. It's a handful of kind of cherry-picked cases, a short time series of throughput and latency, and I think to make a convincing case, you really need to demonstrate the behavior across a much wider range of scenarios and present the data in a way that's more useful for comparing performance. So, CDFs of latency are nice, especially looking at the tail latency rather than just trying to pull numbers off of a short time series.
Well, there's only so much we can present in half an hour. In any case, the code is available. You can run whatever tests you like, and you can also ask on the mailing list for more data. I'm sure we can accommodate you.
Okay, thanks.
I'm going to suggest that we switch gears to the L4S status. Would you like me to share those slides, or does someone else want to try to project those?
Wes, if you can do it, please.
Yep.
And Bob, your audio is much improved. Thank you.
Okay, yep.
And can you see the charts?
I can, yep, thank you.
Okay.
Right, so I was asked to do 5 minutes on an update on where the drafts are at, and then about 15 minutes, I guess after questions on the first bit, on where the implementations are at. And that's going to be a joint presentation with Olivier or Koen. Right. So the architecture draft and the L4S architecture draft and the L4S identifier draft have both just been revised and submitted in usual just-in-time fashion. I think it was 2 minutes before this meeting, maybe 3 minutes for one of them. So I'm sure everyone's read them because they're quite short. Sorry, that's understated British humour there. And the main third L4S draft, the coupled dual QA/QM, is in pretty good shape when we had a look at it. Had other people review it and couldn't find anything particularly wrong with things like terminology and wording and things. So we've got some updates to do to that, but we'll do them in the next few days, maybe a week or so. And just there's been a number of updates across both those two that I've said are just submitted, and then I've got another slide on specifics. And the main cross draft updates are to define scalable congestion control, expressing it in terms of an invariant recovery time, rather than as previously based on its response function, calling it 1/P is more the means to how you get the end, and the end is invariant recovery time, so that the thing stays scalable at all flow rates. And this is something that's really the essence of what we're trying to get out on the internet, is the ability to have a congestion control that can continue to scale indefinitely, which has been effectively the quest of congestion control people since the unscalability of Reno was pointed out back in the 90s. And then there's a whole question of terminology across the drafts, which we've taken up Michael Schaaf's suggestion, and Greg is going to talk about that later, so I won't go any further into that. Then we've also turned anything that we perceived as hype or other people perceived as hype into more precise statements. So I'd ask those that didn't like that, the style, to if they could have a look again. But this time, I mean, last time I said we can probably find the hype ourselves, no need to list it all. But if you can now suggest text or identify where the problems are if you review it again. I'm thinking particularly of Jake, who was particularly concerned about that. Okay, next. The two revisions in slightly more detail. They're both major revisions. If you look at the diff, it's sort of maybe about, 10% coloured. But no, not that bad. But 10% of lines maybe, but not 10% of octets. So the architecture draft, we've explained how L4S works with FQ and dual Q better because it was a bit high level before, or a bit too high level. We had people not really, or wanting to know more rather than just referring off to other drafts. And fixed cross references to later, which no one knew where they were, later in quotes, and loads of other minor edits. So the architecture, pretty happy with that now, except for the abstracts. Really, it's still far too long, which was a criticism Jake gave to it, and we've taken the hype out of it, but we've not been able to make it shorter. So we're hoping to work on that in the next few days, and then put another revision out, just because we ran out of time trying to get a decent abstract. So that really saying you can start reviewing it, but don't review the abstract for another few days. Then the ID, the identifier draft, that is intended for experimental specification. This is the one that we have currently saying, defining use of ECT1. So this is the key one for this meeting. There's a few changes. Loss recovery in time units, as promised in the last Singapore IETF meeting, they've changed the must on that to a should, and made argumentation afterwards consistent with that. And there was also another must, I noticed that was actually wrong. It went in there right in the early days, probably about 5 years ago, and it said you must mark ECT0 packets under the same conditions that you would drop not ECT packets, and that's sort of stronger than even RFC 3168 says, because 3168 doesn't say you must mark ECT0 packets. It just says, you know, if you support them, you must. So we've said if you you need not mark ECT0 packets, but if you do, you do so under the same conditions as you drop not ECT packets. So that was just a bit of a gaffe. And we were asked to add information about how to monitor deployment of L4S for any harm on the internet, any harm it might be causing. So I've added a bit on that, and then loads of other minor edits. So I think the identifier draft, I'm happy with it now, but it needs reviewing. There's just two things I'd like to add, and in addition to that, there's Jake has asked if we can add some material on at least documenting an SDE-based alternative. So I've got a response back on the list. The other things I'm not happy with that may need to be added, after a review by Brian Carpenter, put in some wording he wanted, which was recommended standard use for instead of global use for diff-served code points. But unfortunately, it's not just about diff-served code points, the section they're in. So it makes it look like any identifier is recommended for standard use, which it just, I don't know quite how to get around that. It's a bit of an awkward wording anyway, because it makes it sound as if it is standard already. Yep, David.
Bob, this is David. I can try to help with that. I understand where Brian's coming from on that one, and yeah, you're digging in the right place where that particular concern is specific to how diff server was spec'd. I'll volunteer to help with the text. Also, I'm going to assume that when you work over the need not mark ECT0 package green text, that will turn into a should or a must, right?
Oh, well, the must is earlier in the sentence. That's why I didn't quote the whole thing here.
Okay, but you just reading on the slide, I'm assuming that in the PowerPoint to draft compiler will get suitably rendered somewhere as a must or a should.
Yeah. And yeah, so that's that. Any questions? Okay. Shall we move straight on then? Right, so there's not much to say about the AQM code for this meeting. Dual pi squared and FQCODL, we haven't really got a name for it, FQCODL TH for threshold, FQCODL with a threshold. That code is stable. I mean, the FQCODL threshold code is easy. So all the AQM code is really quite stable. That's the open source stuff. We continue to use it to test TCP Prague against. There's other implementations ongoing that are more product-based, closed source-based, and I'm not going to talk about them here. I'll gather updates on those for Vancouver. Hang on, just go back. So here, I'm only discussing the reference implementations of TCP Prague. Our reference implementation, I should say, and again, I'll gather update reports on other implementations for IETF 107. Next. So this is all about the TCP Prague Linux reference implementation. Just a reminder slide of the requirements we have in the ECN L4SID draft and the optional requirements or optimizations that are going to be needed. The requirements are for sort of safety and the optimizations are performance improvements. And then I've got those repeated. I'm not going to read the left-hand side of the slide. This is a copy of an earlier slide. But they are requirements that we've set ourselves and other people set back in 2015 to make scalable congestion control safe on the internet. So next slide. So that was the status of this chart, this traffic light chart in November 19. And if you want to flick back and forward with the next chart, which is the status now, they should you should be able to see the differences. And the main focuses are in the text on the left. What we've been working on is the text that is not grayed out. And you'll see that reduced RTT dependence, we've now got that running and working, and going to be talked about later. And also the classic ECM bottleneck detection code, we've got that working and evaluating it on a wide range of cases. It's in progress. We should definitely have that all sorted soon. And I'm hoping, today or tomorrow, once everyone on the team's had a chance to look through it all, we can post a large set of results on that, something like 4,000 different scenarios with all the plots of that. And I'll now go through very quickly some of these, but focusing mainly on those two that say evaluation in progress. Next. So this is the first one that's the major outstanding issue number 16, where the problem is if you have a 3168 ECN in a single queue on the internet, you get this potential unfairness between L4S and classic flows, because the TCP Prague or the L4S congestion control is much more aggressive, and that's the whole point of the other isolation solutions. But if you haven't got that solution at your bottleneck, the idea is that the end system is meant to detect that it's in a 3168 bottleneck and start behaving more like 3168 would expect it to, not L4S. So here you see roughly, I don't know, 12 times unfairness in the middle of the plot in the worst case. This is the sort of thing that was being mentioned earlier. You need multiple link rates and multiple round trip times, and you need to show where the mean is and some whiskers to show what the typical deviation is across a number of tests rather than just one, what Greg called cherry picking tests. So next.
Bob, can I just clarify? Is that similar to the plot you showed in Singapore?
That's identical. This is about the problem. This isn't the solution yet. As I say, okay. we want to summarize all these 4,000 scenarios we've done into those sort of plots, but we've just got to run that all through.
Okay.
And we're still tweaking things because this is a heuristic algorithm. It's not what I would say. I wouldn't say it's an elegant mathematical algorithm. It's purely based on finding a sweet spot. So just a brief outline of how it works for those interested in how things work. It's not modal. It doesn't just switch between scalable and classic. It's score-based, and it transitions between the two, as you can see in the picture, which I'll describe in a second. The detection algorithm drives the score on the horizontal axis based on primarily passive detection to start with. And that in turn is primarily based on delay variation, on the basis that if you're in a shallow queue, you're going to get less variation than if you're in a deep queue, but with some possible exceptions to that. So it actually uses a number of other variables. And the aim, and so far we've managed to keep to that aim, is to use metrics that TCP is already gathering. So we're not having to add extra code for these metrics. We're just having to collect them together and calculate based on them. We may have to alter those metrics, for instance, averaging them over different time periods than TCP is, but at the moment we're just using the base stack metrics. I can talk more about IETF detection later, but we haven't done anything on that yet, so I'm not going to talk about it here. And the point here is that this gradual changeover is because detection isn't likely to be perfect. We don't want to suddenly switch to another behavior. So if there's a brief period where the algorithm's getting it slightly wrong, it will just slightly push towards the other behavior and then it will come back again. And if it has transitioned right over to classic and there's a slight period when things look a bit more scalable, it won't immediately jump to the other side. It might transition a bit, but then go back to classic. And we can see that happening in the tests. And I'll post after the session or in a couple of days' time all the tests so people can see this classic ECN variable that's in the horizontal axis there, how it moves in as it's the classic bottleneck is detected. So just to be clear, it always starts as scalable, and we can use the per destination cache to record what appeared to have happened for this host before, and so it may not start as scalable. If last time it ended up looking classic, it could start straight as classic. But it starts as scalable because, to be honest, the behavior isn't that worrying in the first second or so. For fairness, you're talking about long-term fairness for long-running flows, not really about dynamic behavior. And it starts maintaining the scores straight away, from the first CE mark, but it maintains the underlying metrics right from the start. And the reason for the algorithm behaving like in the plot is so that it doesn't immediately jump. There's sort of two areas of hysteresis at either end, where it starts at the green dot, and it will still be fully scalable quite a while before it then starts to transition. So it's got these sticky areas at both ends, and I'll describe the plot now actually. So the x-axis is the score based on the metrics that it's measuring, which I've got on the next slide, or the slide after, I can't remember. And vertical axis is the this value C, which is which behavior, that's what drives the behavior. So from 0 to 1, and if it's 0, it's scalable, and if it's 1, it's classic. So that's where you get your hysteresis from, by having this sort of piecewise ramp. And it will move faster across the transition the more strongly classic is detected, or clearly move faster the other way if it was classic and it detects that it's really gone strongly scalable. And there is an assumption that classic fallback only becomes important for longer flows. So I want to repeat that, and if people want to comment on that, please do. Okay. Next. Right. So here's just a code snippet, pseudo code snippet actually. So the idea is, I mentioned it, transitions. Well, what does that transition actually do? It's all in that last line. When you do the SS stress reduction in TCP, then instead of, like in TTP Prague, it says reduction equals Cwin times alpha over 2. Well, instead you do the max of alpha over 2, which is the Prague one, and C times the alpha, the fixed alpha you get for a classic congestion control, and we use ABE as that congestion control because this is ECN. And so it will, so once the thing has moved over the classic, it will give you just full solid large saw teeth as you would get with ABE. And if it's at the other end, you'll get adaptive saw teeth, which is what you get with Prague. They're shown small here because they usually are, but the whole point of it is it's adaptive, so they can go large, and in fact they can go larger than ABE, and that max will pick that up, and so it can respond faster than ABE would when it's going down. Then just to point that that's an active link in the slides to the paper on this, and we will put either the results in that paper or a link to the results, or probably both. Put a selection of the results in and a link to the full set, and it gives the rationale for it all and everything. So next, one level deeper. I think we're running out of time because we want to talk about RTT independence, so I won't go one level deeper, but you can read this in that paper I just pointed you at. Next. Oh no, I guess that is important to say it's working. Assad, I don't know, Assad, are you on the call? I haven't seen.
Yes, I'm on the call.
Do we have time for a demo, or should we maybe do the do your bit of the talk and then see if we've got time for your and our demo and decide at that point? I don't know. How are we doing for time, Wes?
I don't think we have a lot of time still, right? So I have to hurry through the slides.
We have 30 more minutes scheduled.
Bob, there's a question in the chat which you might want to take up offline because it looks like a rat hole invitation. In essence, there was a comment of hysteresis and risk for oscillation, which I think is going to boil down to explaining what the damping properties are of this control loop if you attempt to drive it into oscillation.
Yeah, I noticed Ilpo said it's not actually hysteresis, and that's true. It's stickiness, not hysteresis. Sorry, wrong word. And if there's an oscillation within one of the sticky ends, nothing happens. If there's an oscillation into the transition area, the whole point of using a transition rather than a modal thing is it will just give you a slightly more classic than scalable congestion control as it goes through those oscillations. It's not, that's the whole point of it not being modal.
Understood. Please take. I would just take this offline because there is a concern about when you have an oscillating control loop, whether the oscillations are stable and increase, or whether the control loop has damping properties that will tend to damp out the oscillations over time, and that's not something we have time to dive into in this meeting, I don't think.
Okay, but very briefly, it's essentially steps. Every time it does every round trip time, it will push more or less one way depending on what the measurements are. So it's damped in that sense. It doesn't jump straight over. The score has to be high every round trip time for it to keep moving in one direction. Right.
Bob, can I also say for this issue is probably one of the most important ones right now, as I understand. And so it should be probably homework for people to check out your paper you referenced and see if this is starting to be compelling or what more needs to be done towards closing out this issue.
Yeah, just at the moment the paper is just the design. There's an evaluation section that I left as a placeholder in there when we first wrote the design that we will fill, but it's not got the evaluation in yet because we're just completing it.
But people will have to understand the design in order to make sense of the evaluation too.
Yeah,
please
so,
make
sorry, when I posted it, I did ask, please do criticize the design because that's the best time to criticize something, not wait until it doesn't work. So if you don't think it's going to work or whatever, go ahead and look in there and tell us what you think might be better and so on.
And please make the code available. Some additional eyes on the code will find the corner cases.
Okay, I'm going to hand over to Kuhn, and then we'll see what time we got at the end for demos. I think it's the best way to do this.
Okay, so maybe the next slide. I'll try to go fast through the presentation. So the problem with round-trip time dependence is that the smaller the queues and the latency become in the internet, the bigger the difference between the smallest and the biggest round-trip times, and the more unfairness. And in this first slide, you see that over time, queuing delays became smaller and smaller. Tail drop has 200 milliseconds. And if you compare then a flow with a base round trip time of 15 milliseconds and 0.5 milliseconds, the ratio is about 1 to 30. And without any queuing, you would expect they have indeed a rate of 1 over 30 as a factor. But with a 200 millisecond queue in between, you see it becomes only 1.1. And the smaller the targets become, the bigger this rate unfairness become. In the worst case, let's say, or in the most challenging case where we have in the Alvarez AQM a step at 500 microseconds, around 500 microseconds, we get a ratio of 15.5. Next slide. So there is also the argument, okay, we have in the dual queue two different targets, two different queues. So also there, with the same base round trip time of two flows having the equal base round trip time and using the different Alvarez or Classic, with the different queue targets in the middle, they get similar unfairness. So it's not only a problem, let's say, of the AQM, which cannot know what is the round trip time of the flows. On the other hand, it's also a problem for existing TCP already. So a common solution would be nice. So the next slide. We developed a new Prague add-on to steer the round trip time dependence. And this code is available and will be released soon. We also recorded the demo video, which we can show if there is time. So the goal is that Prague, instead of the rate, which is proportional to 2 divided by the probability and the round trip time, this round trip time can be replaced by a mapping function, kind of target round trip time function that you can define inside Prague. So for instance, if we would define this function as a function of the round trip time, can be any state, but in here we just use the round trip time again. If we just add 14.5 to the round trip time, you will see the problem is solved, right? And this is also what we can demonstrate that this really works. But of course, is this now the magic equation that we want to? And that's a little bit the discussion, maybe in the next slide. You see there are different reasons why we want to have a smarter mapping function, round trip time mapping function. So of course we want in a long-term throughput balance with other round trip time flows. So flows having a different round trip times. We also want to handle shorter flows faster, typically because we have a shorter round trip time. We can handle them also faster and accelerate faster at smaller round trip times. Well, there can be many ideas behind this. We have been exploring already these things, and it's all possible. The only thing is, of course, the question is this smart function. Do we decide that as an IETF, or is it the application dependent, and can applications decide on this as well? So that's probably the discussion we have to go through in the future. Anyway, the next slide. So just to give a small overview on what is actually done, what is changed in TCP Prague to have this round trip time dependence. So the first point is that we control the additive increase to behave as the target round trip time flow. So we trigger the same amount or frequency of marks as a target round trip time. We leave the multiplicative decrease unchanged, so preserve the responsiveness as much as possible to preserve the low latency. And we also, if we change also the EWMA update frequency to the target round trip time, then we also ensure that they converge to the same alpha, even on a step, because there is a different behavior on a step and on a random probability marker like a pi controller. So all of these situations we got managed. Next slide. There were a few tweaks that we also had to correct or change a little bit. So to have a more smooth throughput also and a better stability, we modified the base behavior of data center TCP, which does not increase for a full round trip time. We changed that to become more smoother and only increase when packets are not CE marked and not increase when packets are CE marked. So it's also better to support the unsaturated signal more smoothly. And then also an important thing is that for these smaller Windows updates, we also had to modify how these small, we had to carry these small updates over different round trip times. So the remainder of successive congestion window increases and reductions was important to make them more fine-grained. So, because if you have a small window and you only have to reduce 3%, it can be a third of a packet. And if you don't keep this reduction of third of a packet over different round trip times, you're not going to increase increase or also decrease. And it's going to be changing, let's say, the equation. So this is also handled, and in this case, we get a perfect controllable round trip time dependence, let's say. Next slide. So we have a demo. It's a 2-minute video that we can show if Wes can show it.
Yeah, let me attempt that a second here.
If there in the meantime are any questions?
I was just going to say, Assad has said that he can't get the GUI working at the moment, so you've got a bit more time for your demo, and we'll have to do ours on a video for the fallback.
Okay, yeah. So I can do the video now, right? So this is the typical GUI that you use on the testbed.
Let me know when you want me to hit play.
Yeah.
Can I ask a question in between?
Yeah, sure.
Okay. So this looks great, but how will you make sure that this increased RTT independence of TCP Prague actually will solve the dual queue problem? Do you have any plans of making TCP Prague mandatory and enforce that for admitting in the LLQ, or how do you want to deal with this issue?
Well, it's enforcing. I think my take on it is that enforcing is something that can be done, but it's not, let's say, should not be mandatory, because the internet today.
Okay. Let me try to expand on this before you answer. The issue is, and I'm not sure whether everybody is conscious of that, is that the dual queue sharing between the two traffic classes is approximate. And this is evident by the old TCP Prague behavior without the decreased RTT independence, that at short RTTs, the LLQ will crowd out traffic in the other queue. And you argue that increasing the RTT dependence is the solution to this problem. And this is fine. All I want to know is how you make sure that all the flows that actually go into the low latency queue and can crowd out stuff in the classic queue, that all of these flows actually use a transport that's sufficiently RTT independent so that you have the guarantee that's required. And I only see some sort of admission control, but please go ahead.
No, it's the same question. How can you guarantee that today somebody is not using a congestion control or a TCP without congestion control? Do we have on each bottleneck a policer? No. Do we have in the network at the right places polices where it is important to protect, for instance, between users? Yes. So it's not a generic mechanism for an AQM to assure policing. It can be added on top, and it will be added on top where it is important. Where it only hurts yourself, probably operators won't invest to put a policer or an FQ or whatever. Of course, if you want it yourself and you're using applications that are not responsive or whatever, of course, in your benefit it might be, but so it's
my concern. Cool. My concern is not an AQM under my own control. My concern is a badly managed AQM somewhere upstream of me, where I have to live with the bad consequences of a somewhat unsafe design. And I just wonder how you can make sure that this thing, which is known to have potential side effects of starving classic traffic, how you can make sure that this is exceedingly unlikely. And just telling me that some operator might do this is not going to give me a warm, fuzzy feeling.
Well, it's today, it's the same as it is today. And people get internet access and applications work. And there are applications which are unfair at a certain moment, but there is, let's say, social pressure and people notice this and will make noise about it and applications will adapt.
Okay.
Can I just reinforce that?
I don't hear a discussion that sounds like it's likely to conclude. I think each of you have made the point, and right at the minutes we somehow right at the minutes we'll try to take note of this.
No. Okay, maybe.
Sorry here. I understood that LFRS was going to specify this for the transport behavior. Is that correct?
Yes, we define it as the LFRS requirements, let's say. So there is, let's say, a standard that says you have to obey this requirement.
Okay.
And it's up, it's up to policers if you really want to police it. Well, anyway, that's the same discussion.
The fixing thing is a separate topic. That's fine. Just be clear that the requirement is that the traffic should or even must use this.
Okay.
Right. And the flip side that's being raised, as I understand it, is okay. Requirement written. How will we ensure or make it highly likely that what we write as a requirement is actually observed in practice?
Similarly, how do we ensure that TCP friendliness is observed in practice? We don't, but it is.
Yeah, and okay.
It's based on measurements that individuals do and report this to let's say the community to make fuss about it if people are not obeying the rules.
Write the minutes up. We'll try to make a note that this discussion will continue. Is it time for the video?
Yeah. So we first show it's a dual pi square AQM.
It start.
Yeah, it's a dual pi square AQM, and we will at the top use first Prague and at the bottom cubic, and first show the problem. Let's say that it's not round trip time independent, and if we use then the Prague with round trip time independence, you'll see that the problem is solved. And it's just this equation which is just add in the end system. With this mapping function, this target RDT mapping function, just add the difference between the queues of the queue targets. Okay, if you press play, Wes. Okay, so you'll see first we start a cubic flow, and we add a data center or a Prague flow to it, its round trip time is 0 milliseconds. So you see there is quite a bit of rate unfairness. When we click window fairness, the bottom up at the bottom here, we show in the display instead of the rate, the window, and you see that the window fairness is more or less still obeyed. That's normal, that's expected. If we increase the base round trip time, the window fairness is still obeyed, more or less. Cubic is a bit slower. So if we switch then to rate fairness, you will see with a bigger round trip time, base round trip time, the difference between the flows is less. So this is what is today. It's, I think, acceptable. Both flows work, but it can be improved. So if we go back to 0 millisecond base round trip time and use the Prague round trip time independent Prague, we again start a cubic flow and a data center a Prague independent flow. You see the rate now is fair. So it doesn't matter what base round trip time we take, because the Prague has this mapping function to add 14 or 15 milliseconds to its measured round trip time, and just behaves the same like a classic flow which experience the real 15 milliseconds more. So this could be a solution. As you see also, if we change the number of flows, it doesn't matter. It still all converges to the same throughput. The only question is, of course, now, what is now the best mapping function? And I think this feature, let's say, can solve a lot of round trip time independent problems, and I think we should make use of it. That's it. If there are any questions? It works actually very well. So, and we tested with a lot of different functions. You can even hard code, like we want to have the round trip time dependent to 15 milliseconds all the time. You just put a constant of 15 milliseconds there, and all flows are fair to 15 milliseconds.
There's a question in the chat. There's a couple of questions in the chat. I don't know whether you want to address them before moving on.
If somebody knows immediately which questions there are. Okay, what if the round trip time of the other flow is larger? I see there, and that's of course again, this is a solution with this round trip time plus 15 milliseconds, which still not solves that there are differences between different times. So a better solution would be, let's say, let's make Prague round trip time independence to 15 milliseconds or 5 milliseconds, so that all flows are round trip time independent to a number. Okay, the others, they are still round trip time dependent, but it limits at least the difference between them. And potentially new classic congestion controls could also use the same mechanism for round trip independence, actually, because it's independent from data center TCP, the way we have implemented it, more or less. No.
So just to be clear, you're going to share the video somehow with people on the list, and they can view it at their leisure, and we can talk about it. But since we're getting close on time, I just wanted to suggest that if there are particular things that you want feedback on, maybe focus on those for the next 10 minutes.
There's another couple of update slides, but they only take 2 minutes. Can I just go through them? Yep. We can upload this video to the, I think I've still got access to the right site, so we can put it on the RFS landing page.
Yeah, we'll share the link later.
Yeah, this is just to say, Ilpo, I noticed, is on the call. He's implemented the full spec that's being dealt with in TCPM for the accurate ECN part of TCP Prague. Previously, the TCP option part wasn't implemented. That's based on Olivier's and in turn based on Mia's implementation. He's sort of fully refactored it for upstreaming. He's also found some review or given some review comments on the design, which we've tweaked as a result, and we've still got some ongoing discussions about that tweaking. So the immediate plan is to upstream that to Linux, and Accurate ECN is sort of independent of L4S. It's needed for other purposes as well, like in DCTCP itself. I know Microsoft want it within their data centers, so this isn't necessarily part of the L4S SCE controversy. So that's that. Next. And also, we've been focusing on the faster flow start and faster additive increase, and that's faster flow start without overshooting, without getting more latency. We've demonstrated this a couple of times and presented it in ICCRG and written papers on it, a thing called pace chirping, and Joachim has now merged that into the TCP Prague code over the latest Linux kernel. It's an option and it's default off, and we do want to start using this to do a lot of our measurement tests, because the startup of DCTCP is frankly awful, and this is a lot better. But also, pace chirping can be used by other congestion controls as well. You know, it can be used by Cubic, by Reno, by anything, because it's delay based. It's not ECM based, so it's a better startup for anyone who wants to use it. And the immediate plans are to re-engineer that code, because at the moment it's research code, so it can be upstreamed as well. Okay. I think that's all. Yep.
There's a recurring theme in the chat. Please make sure to make all this code available so other people can work with it.
It is available. It's been available for nearly 18 months now. And I do get fed up with people saying, can you make this code available? And then they never bother going and find it when we tell them where it is. But yeah, okay. I'll tell you again where it is. And it's always been available.
Let's post the list and make sure that based on this discussion, everybody's got access to all of the code that went into everything that was shown here.
Yeah, the ECM fallback, I noticed a similar comment. That is not in a public repository yet, but it will be hopefully in a few days when we publish all the results as well.
Cool.
Yeah, we presented pace chirping at NetDev, Linux NetDev last March, and the code was available at that time and had been for some time. Right, that's just a spare slide. Don't worry with the spare slides. So you wanted, you said you got 10 minutes for something. Did you want to go straight to these slides then, or?
Well, Bob, I've got
running ahead or what?
I've got two other decks from one from Greg, where he can show his newest copy himself, and I've got this other one you sent me with 9 charts on CE ambiguity. So it's up to you what you want to use.
Okay, well, we'll go through this then. Yeah, Wes wanted us to just top off this discussion by going through all the issues, all the open issues. I wasn't quite in agreement on the grouping, but I unfortunately didn't say this early enough. I think number 17 has either been closed or is not being disputed that it should be closed. There are a number of related issues, 22, which really goes better with this set, but it was the way Wes put them out. So we'll keep them the way Wes did them, but just bear that in mind. So I'm going to cover the 3 underlined. Carry on. Yep. So issue 16 is the classic ECN fallback, and I've added in brackets FIFO to the subject line of the issue because it, as was just pointed out in the chat, This problem only occurs when you've got 3168 in a shared queue, not in a F queue. And I'm quite happy for this issue to remain open until we've demonstrated the classic ECN fallback works reasonably well, and we're making good progress on that. But you haven't seen any evidence of that yet because we didn't get to show the plots, but we hopefully will in the next few days. No, we'll go back. The issue actually is two separate issues. It's about, is this problem prevalent and is there a solution? And both of those are moot if the other one is not true. So if the solution works, whether the problem is prevalent or not isn't so important. And similarly, if there's no prevalence, the solution is moot. So I would encourage those that are looking for this problem to see if they can find any evidence of it. I know Apple is still trying to find the problem, and in the data they presented a couple of years ago now showing where CE marking was on the internet, they've found the larger parts of that were due to diff-serve mangling, not ECN. But there is CE marking out there. We just need to find some that's in a single queue. Because I must admit, we're taking quite a bit of time working on this classic ECN fallback thing. So I won't say I hope there's something out there that needs it, but it would be a bit of a waste of time if we don't find any. Detailed solution design, as I say, was posted, and that was in the earlier slides, and it's implemented, being evaluated, and working well. We're distinguishing dual pi squared and CODL. We're using CODL as the primary classic congestion control, and I mean CODL, not FQ CODL, because that's got it sort of pushes the target down lower than others. So you've got less utilization, but lower queuing delay, because that's the more challenging case that makes it look closer to L4S. So that's our sort of most stringent test. I've noticed this question of prevalence. Does anyone want to say anything about that, Rod or Jake?
If you, if you want me to so there are many single queue AQMs that are disabled. It's reasonable to suppose that they have previously been disabled because of the lack of ECN capable traffic, which has changed materially in the last few years. And I think that it's a mistake to consider it the solution moot if there's no prevalence. Just because we cannot observe prevalence does not mean that, if we adopt this position, particularly as sort of part of the adoption of an experimental RFC, I think it countermands previously established IETF consensus that AQM is beneficial. And I guess I'm not sure if you want any elaboration on that, but
that's fine. I mean, I agree with you in theory. That if there's a standard out there and it's not been deployed as a single queue solution, that it could theoretically be deployed, but we can't sort of stop the world for every possibility. There's other examples of things that have been deployed, and sometimes you have to take a punt. Basically, if something has not happened, there's some point at which you have to say, okay, this is not going to happen.
Sure, and that's reasonable, except that I think in this case there are many solutions that are in fact deployed. Like it's a single queue Pi is available today in Linux, so anything Linux based doing some queuing stuff. Additionally, we see it in I think it's on by default in it's present by default in many Cisco devices. Like, it's not so clear to me that that it's correct to call this undeployed rather than unenabled.
This is David. We're unfortunately at the top of the hour, and I'm unfortunately scheduled back to back, so I have to drop right now. Any last final words, Bob, before we wind this one up?
Yeah, I wouldn't mind going to issue 20 because I couldn't hear what you were saying the whole time. So if you can go one more further, and I couldn't say what I wanted to say. So all I wanted to say about the whole big question on the L4S use of ECT1 and the SCE use of SCE1 is that I don't think the question here is whether SCE precludes, whether L4S precludes SCE. It's whether there's anything the community might want from SCE that it can't get from L4S. I don't think we need to just allow two experiments or somehow bend over backwards to allow two experiments if they're both aiming to achieve the same thing.
I don't think we can. I think the crucial observation in there, and unfortunately I'm going to get last word in and drop, is that what the two experiments propose to do are make fundamentally incompatible uses of ECT1, and we will have to select one of the two uses. It can't be both an input and an output to the network.
Yeah, but the point I'm trying to make is that people don't get a right to have their work recognized at the IETF if it's doing what something else does. You know,
boy, do I not want to go down this process rat hole. I'm sorry.
Okay, right.
All right. Okay. That I do have to drop because I am scheduled back to back. Thank you very much, everybody. I've taken a few notes on crucial topics. Chairs will get together and we'll figure out how to issue some brief minutes.
Okay, if we can go back one. Thank you, David. I'll just cover off the other one, which is about C code point semantics. So issue 21 was raised as a general concern about the ambiguity of CE, and two specific concerns have been raised. That is the classic ECM fallback and the issue 22 about reordering. Oh, it mentions reordering. And I believe number 22 has been addressed. Greg's going to come onto that one. So I just don't believe that we need a sort of placeholder for other issues, given everyone's had plenty of time now to raise specific issues. So I don't think 21's needed anymore.
Bob, let me just say, like, procedurally, I think we lost David and we lost a few other people. So we probably should consider like the official meeting over, but I'm happy to leave the WebEx up if you want to have like a virtual hallway conversation about the issues with whoever wants to hang on.
Okay.
So you could. So with that said, feel free to keep going. If people are available to participate, stay on the line.
I think it might be useful to do that for people who are interested, and we can